Welcome Mechanics of Materials students. This is our second lecture on twisting or torsional strains, in this case of circular shafts. So in our previous lecture we derived expressions for applied moment, twist angle per unit length of a shaft, moment of inertia, about the axis of the shaft, our IZZ or polar moment of inertia, and our shear modulus. So now we can relate what's effectively strain displacement, shear displacement in the form of our twist angle per unit length, our shear stress, which is related to ultimate material capabilities, shaft shape size through IZZ and shaft radius, and of course our applied moment, which we can designate, limit, or determine what needs to be applied. So we're just going to point out, some generalities that we can express based on these three different ways to state these relationships. I've kind of highlighted our three different expressions, which are basically all equivalent and just rewrites of one another, but emphasizing, hey, if you want to know how much torque you're going to apply to your shaft, that you would need to apply for a given shaft size, material, and desired angle of twist, you've got this expression. If somebody tells you, hey, here's how hard we twisted something in terms of our applied torque, here's the shaft radius, shape, length, and material, here's the expected rate of twisting. In that case, you wouldn't need to know the length. You could know the twisting per unit length, and then you can multiply that by the length, and you get the actual angle of twist. And then if you said, hey, I want to limit my shear stress to XYZ, which would represent maybe a yield with a safety factor, then I could see what combinations of radii and applied moment I could tolerate. And I just say radii because IZZ is only a function of radius in this case, if it's circular. So what that tells us is the rate of twisting, which is that d phi dz, is proportional to applied moment. So directly proportional. So the more I twist it, the more torque I apply, the bigger the twist angle per unit length. It's inversely proportional to both the modulus and the moment of inertia. So if I want to design against a twist angle, I want the shaft to stay straight and not twist, then I would go with a bigger moment of inertia, which in the case of a circular shaft means a bigger radius, or placing more of the area at a bigger distance from my center. So maybe a tube instead of a solid shaft if I'm going to go with an equal volume of material, and go with a material that is literally stiffer in shear, so a higher shear modulus. So I can change the material, or I can locate more of my material cross-sectional area at a bigger distance from my center line. So, tube or a stiffer material. And I can see that my shear stress, looking at this equation, increases linearly with radial distance from the shaft center for any given moment of inertia and applied moment. So if we're looking at where's it gonna yield first, how would I calculate that, or where would I look for that yield? It's going to be out on the outer radius, which is super convenient if I'm going to measure max shear strain. I'm going to be encountering that maximum shear stress at the outer radius, which is a very convenient place to attach a rosette strain gauge. So I can use all of these trends to give me a design guideline or an analysis guideline. So what if I wanted to get some real numbers? I have an actual shaft length. It's 10 feet, it's 4 feet, it's whatever, and I want to know what the angle of twist is. I can take my expression here, that is the rate of twisting, and just integrate both sides. So I can say that my d phi from some starting angle, maybe unloaded, to another angle once I apply moment, I'm just going to add up along whatever length of shaft I'm concerned with, maybe the whole length. My expression dz over shear modulus times izz, and I'm going to integrate that with respect to z. Now my polar moment of inertia is only dependent on R, not Z. So if I'm not changing applied moment as I go along the shaft, I'm applying moment maybe only at the end, so the moment is uniform over the whole shaft, and I'm not changing materials. I don't have some kind of reinforcement material which is more dense at one end of the shaft than the other. If G is constant, then I can take this whole expression, this quotient, out of my integral and just integrate from 0 to L dz, which just gives me L. So my delta phi, my angle, subtended angle that of twist for the whole shaft length is just going to be the shaft length times my applied moment divided by polar moment of inertia and shear modulus. So for any given shaft length, I can get the actual angle that I've deflected. So let's take a look at a really quick example of that. So we've got a brass rod and it has a 20 millimeter radius. It's solid, so my moment of inertia is just going to be pi times that radius to the 4th times 1/2, which in this case gives me 2.51 times 10 to the minus 7 meters to the 4th. Brass, I can look up in a table. I looked up in a table in the back of a strengths and materials book and got 37 gigapascals. So that's a little smaller than what I would expect for my tensile modulus. Usually shear modulus is a bit smaller. So if you're familiar with the E, the Young's modulus, being in the 70s, having a shear modulus in the 30s is probably pretty expected. We were told that the shaft is 1 meter long, and it's getting a twisting moment, and I wrote as opposed to bending, because of course we can bend something. We hold up to the camera. We can bend something, and that's a moment, in in a different direction, or we can twist it. We're only looking at twisting. We're assuming that this is being held up and that there's no loads, no bending loads. I mean, obviously the shaft has weight and it's being supported between two bearings. There's a little bit of bending, but we're assuming it's driving something. And so the twisting moment, so the moment in the z direction along the axis is like huge compared to any flexural moments. So it's 1750 Newton meters. And somebody wants to know, hey, what's the shear stress, max shear stress in that bar? We want to make sure it's not going to yield. And what's the angle of twist? We want to make sure it doesn't twist more than we can tolerate, sliding in a bearing or something. We want to limit the angle of twist. So all we have to do is deploy our different expressions for what we care about. We can go through the derivation, but maybe take these expressions and write them down on a little handy deployment card, and you can use your units to check to make sure you're deploying it right. But we know that our tau max is going to be found at R max, so at the outer surface. So we know it has a 20 millimeter radius, so our tau max is going to be at 20 times 10 to the 3rd meters. So we just put that particular R into our tau as a function of applied moment and moment of inertia, and we get 139 megapascals. And we would take this and we would compare it to the shear yield stress for the material. So if we looked in a handbook and we found that the tensile yield strength of this material was 200 megapascals in uniaxial tension, we would kind of plot that on a Mohr circle and go, aha, the max shear corresponding to that is half the max tensile, and find that we didn't yield. So remember, this is shear max. So if you're comparing it to ultimate or yield-based material strengths, be sure you're comparing a loading mode to loading mode. So we can deploy our stress transformation, so we're comparing apples to apples in terms of stress state. Okay, so assuming that we haven't yielded, that this is significantly less than our material yield with our safety factor. Now we want to make sure we know what our deflection is, so we can basically go back to our integral up here. We haven't been told the material changes along its length in terms of its shear modulus. We don't have any step-ups or step-downs in radius, and so we have the same moment along the shaft, the same shear modulus, the same moment of inertia. So we can say that our twist angle is just going to be our applied moment times the whole shaft length divided by the modulus and the moment of inertia, which we have down here. There's our applied moment, whole length, shear modulus, moment of inertia for our given radius, and we get 0.188 radians, which ends up being about 10.8 degrees, which is kind of pushing the small angle approximation. So I would say this is kind of a borderline situation. You can check that conversion on the radians to degrees, but if that's indeed 10 degrees, I would be I'd be maybe cautious about this, because that's a little bit much for a small angle. Probably still valid, but it might not be quite as accurate. So you would, in that case, maybe want to use a bigger safety factor and be conscious of things like buckling, which we'll discuss later. So that's just a very quick, simple example of how we can get, basically we can get stress, shear stress, and we can get a deflection angle for a given total length of a shaft based on input variables that are common or available or proposed. So we're going to stop now, and then we're going to pick up in a follow-on lecture strain energy and other applications that are specific to our very convenient one strain only shear in the Z theta, and see what we can tell from strain energy about our twisted shafts.